Hi guys, so this is lecture 2 in chapter 12. So we're going to talk about object-oriented concepts. So there's several object-oriented concepts that we're going to have to look at when we start talking about collections. So we're going to rely on type compatibility rules, interfaces, inheritance, polymorphism, and we're going to sort of review these as necessary. We're also going to talk about, or we're going to rely on a programming mechanism from Java 5, which are called generics. Generics are actually fairly new to Java in terms of its lifespan. They're actually copied from C++ templates, amusingly, because Java came after C++ and it was supposed to be an improvement. And in fact, they went back and they copied generics from templates because they were just so damn useful. And they are really useful for implementing things like collections and actually quite a few things. Generics are really pretty useful. And I think you've covered generics in 112. So we're not really going to be talking about that. We're just going to be pretty much using them. So generics, so suppose we wanted to find a stack that holds an object references that would allow it to hold any object. We could do this, right? You can, because object is the base class for every class in Java. So if we want to implement this, we could implement this as an object, and then we could stick anything in there, anything in our stack that we wanted to stick in there. And then what we'd have to do when we popped off, we would have to upcast and then check to make sure that the upcast worked by checking to see if the reference was null after we cast up. Sorry about that. But then we lose control over the types of elements that get stuck on the stack. So we lose type safety in some sense because we don't know what you're going to put on there. You could put anything in there if we just use object. And then the casting is kind of ugly when we upcast. We have to check and see if it's null. And if it's null, we have to deal with the fact that somebody stuck something on the stack that we didn't want them to stick on there. It'd be better if we can enforce the rules for how you use the stack using the language. It's much easier to debug something. So if you use the language and someone tries to stick something on there that doesn't belong in that stack, you're going to get a compile time error, right? If you wait until runtime, it's going to be a runtime error. That's going to be a much harder problem to solve usually than a compile time error. Compile time errors are super easy to fix. So we try to make the language do the heavy lifting for us. So a better solution for this is to define a class that's based on a generic type. So the type is referred to generically in the class, and the specific type is only specified when an object of that class is created. So the generic type placeholder is specified in angle bracket in the class header. So we have this class box, and then we have this type T that's unspecified that we're going to use. So any identifier can be used, but we often we use T for type or E for element. You can actually mix these things up. It doesn't really matter what you use for that, but this is sort of the standard. The T is usually the standard that people have, even in C++, they use T. So there you go. So when you need a box and you instantiate it with a specific class instead of the T. So before we had the T, we're going to have a box and we're going to put a widget in there. It's going to be a widget type. So we're going to, when we create this new box one instance, when we new it up, we're going to new it and we're going to say, well, we're going to replace this instance of T everywhere in the class with widget. So box one can only hold widget types now because of the way we've declared it, and we'll have a compiler error if we try to put anything that's a non-widget into the box. So when an object is removed from the box, it's a widget, right? It must be a widget because that's the only thing we could have put in there. So therefore, it must be a widget. We don't have to cast. We don't have to check. Now underneath, what is Java doing for you? Who knows? But we don't have to worry about this, right? The language enforces it. So using the same class, in fact, you can do it in the analysis stage. It doesn't happen at runtime. But using the same class, another object can be instantiated. So in this case, we could put a box with a gadget inside, and we could say this is a gadget. So now the box2 object can only hold gadgets. They're the same generic type, but the specific instance of this is specialized to hold gadgets, right? So generics provide better type management control at compile time and simplify the use of collection classes. Because we can write something like a stack And instead of specifying a type, or instead of using an object as the base for what we're going to put in our stack, we can use a generic, and we can specify when we use the stack what we're going to put in it, and it'll be enforced in the compile time. So we're going to look at stacks. We talked about the stack operations, and we're going to look and see how stacks can be used to help us solve the problem of evaluating postfix expressions. So if you remember a postfix expression, we have the operator that follows the two operands. So where you would write 15 minus 8 as an infix expression, a postfix expression would be 15, 8 minus. And if you've used, there's certain calculators that do this by default. Some of the engineering calculators do this. It's easier to write some of the expressions or put things in if you do this. You don't have to use parentheses because it can be more clearly defined without parentheses. But we can use stacks for evaluating these things, right? So how do we do that? So again, postfix expressions eliminate the need for parentheses to specify the order of operations. So we have this complicated infix expression with all these parentheses and things. We can write it as this postfix expression without any parentheses, and we are good to go. It looks a little weird to us because we, have no idea. We don't sort of think of it this way. But if you did think of it this way, it'd actually be a lot more convenient. But we can evaluate these things with stacks fairly easily. All right, so the way that we do that is we scan the expression from left to right. When you encounter an operand, meaning a number, we push it on the stack. When an operator is encountered, we pop the top two elements off the stack, perform the operation, and then push the result back on the stack. So when the expression is exhausted, meaning we're at the end of it, the value on the stack is the final result. So let's look at some examples of this. So we have this 7, 4, negative 3 times 1, 5 plus divide times, right? Looks really weird. Super easy to evaluate with a stack. We push 7, we push 3, or 4, we push negative 3, right? Now we see multiply, that's an operator. We pop the top two operands, that's negative 3, then 4. We multiply, that's negative 12. We push that on the top, right? Now we see 1, 5, we push 1, we push 5, we see plus. We pop 5, pop 1, add 5 and 1, that's 6. We push that on the top. Now we see another operator, divide. We pop 6, pop 12, divide. We get negative 2, which we push. Now we see multiply. We pop negative 2, pop 7, multiply. It's going to be 14, and we're going to push 14 onto the top of the stack, right? So that's our answer is 14. We're done with the expression, and we've evaluated this, and we now know what the computation is. So this is equivalent to an infix expression with a bunch of parentheses and things that you'd have to look at and figure out how to do exactly. Which we can do too. But postfix makes it super easy because we can just evaluate it directly with a stack. Okay? So let's look at some code for how to do this. The code should be up online. I'll put it up online for you if you're interested in looking at it. You also have the PowerPoints if you want to look at the PowerPoints for this. But we have our public tester class. We have our main, which takes a string, array of string arguments. We have a scanner. So we have our postfix evaluator. So the meat of this here is going to be our postfix evaluator right here. We're going to make a new one of these. We're going to ask the person to enter a postfix expression one token at a time with a space between each token. So it's going to look something like this. For example, 5, 4 plus 3, 2, 1, blah, blah, blah. Each token must be an integer or an operator. We're going to read in a line here in Java, and then we're going to call evaluate on the string that we've got in from that. Then we're going to print, and then a blank line, and then we're going to print out the result of that and ask if you want to evaluate an expression. So this is the driver program for what we're looking at. So what we really want to look at though is the postfix evaluator. So this is the meat of the thing, right? So the postfix evaluator class, we have add, which we define. So we're defining a bunch of constants here that we're going to use in our thing. So we're going to define add to be plus, subtract to be minus, multiply to be asterisk, and divide to be the regular divide. We're going to create a stack. You notice that we import java.util.stack up here. So this is the stack generic. We're going to create a private stack, and we're going to specify that it's going to hold integers. Okay, so this is our stack. It's going to hold integers. We're using the generic here. All right, the stack has been written as a generic. So in our constructor, we're going to create a new stack instance. It's going to hold integers again. And now in our evaluator, what we're going to do, we're going to take this string in. We're going to use this parser, the scanner. And we're going to say while parser.hasNext token equals. So this token is a pretty common thing for people to use when they're doing parsing, which is what we're doing here. We're going through a string and breaking it up into symbols or tokens. So a token is just a piece that has some semantic meaning, right? So in this case, we're either going to have two types of tokens. It's either going to be an operator, or it's going to be an integer, right? So here we're going to get the next token, which is the next piece, and then the delineator between them is the space, right? So that's the default delineator with the scanner. So if the operator is a token, if the token is an operator, using this isOperator function, which we'll define in a second, we're going to get operand 1 or operand 2, doesn't matter which one you call them, but we're going to pop, and we're going to convert it to an int. We're going to pop the second one, right? And then we're going to say, the result is this evaluate operator token dot char at 0 opcode 1 or operand 1 operand 2. So basically this is just going to be, we're going to look up the character, because remember this is character, this token is going to be the string that we've parsed out. It's going to be an operator. So it's going to be one character long because all the operators are one character. So the 0th element is going to be the character, right? So we're going to evaluate single operator, and then we're going to push the result onto the stack. All right. Else, so if it's not an operator, then this thing must be a operand. So it's going to be an integer. So we're either going to pop 2 and then do an operator, or do an operation and then push the result, or we're going to just push what we get. So we're going to take this thing, we're going to convert it to an integer, and then we're going to push it on the stack. All right. And then you're going to return the result, which is going to be whatever's left in the stack. Hopefully that makes sense. So the result here, we're kind of double dipping here, right? Because the result here is going to be, it's supposed to be whatever is left in the stack, right? It's the top of the stack when we're done with the expression. And we're kind of cheating here because we have this result and we're pushing it on the stack, but instead of checking the stack, we're using the fact that the result is still equal to whatever it was that we set it to right before we pushed it. It's kind of cheating a little bit. If we were going to do this and be a little bit more thorough with it, we'd probably need to check if the expression was invalid. So for example, if the expression was invalid, one of two things would happen. Either one, when we tried to pop one of these pops, it would fail, right? Because the stack would be empty, and we would try to pop, and the stack would have nothing on it. So it would be failing because we didn't have enough integers in the expression. On the other hand, if we have too many integers in the expression and not enough operands, what'll happen is down here at the bottom, when we do this return, instead of returning result, we'll check the stack. There should be one thing left in the stack, the answer. If there's two things or three things or anything other than one thing, then the expression was actually invalid, right? So we're kind of being a little sloppy here in the code, but in reality, what we should be doing is checking this too. But basically, we're just looking at the idea. So we're parsing through this string. We're grabbing, if it's an operator, we're grabbing the top two things off the stack, and we are performing the operation on them. Then we are pushing the result back into the stack. Else we are pushing whatever it is that we've parsed off onto the stack as an integer, right? All right. So here we have the function that we're looking at before is operator, and again, this is just if token dot equals, and we're comparing the token to these four strings, which are defined operators. And if it's one of these things, we return true. If it's not one of these things, we return false, right? So that's what that does. Pretty straightforward. So evaluate single operator. We take the operation. We take the int operand 1, int operand 2. We say the result starts as 0. We switch on the operation. If it's an add, we do this. We add. If it's subtract, we subtract. This is pretty straightforward. We use this case statement, and then we return the result. We just do whatever operator it was that we've passed in for evaluate single operator. So this should be pretty straightforward to you guys. So that is the end of what we're going to talk about for now. I'll be back in just a few minutes. Thanks.